And then we'll go into the more interesting part of, say, how does that reflect into how we design our ship, or how we should design our ships. Good. I'll assume you all know basically welding, cutting, etc. If not, I prepared a link for self-study and you can brush up on that afterwards. Let's go into the actual assembly. You typically start with steel parts, profiles, plates, pipes. You cut these to size, including maybe some angles, beveling for welding. And then you move to ever more complex assemblies. First, for instance, you have your plates and you put your profiles as stiffeners on. Then the flat panels and curved plates with stiffeners get assembled to 3D small blocks. Those get to large blocks, and eventually the large blocks typically get together in a building dock these days. So you have this typical hierarchy. You have lots and lots of smaller parts, and that will come in handy later on when we do design for production. Repeatability, reduction of number of parts is a good thing for design for production. Profiles, grid of profiles, put the profiles on plates for stiffened panels, and then get into simple blocks and then to larger blocks. This may look at first a bit confusing, but let's see what's happening here. On the left-hand side, you see that we cut out a funny looking plate and we cut two profiles in length to what they should be. Also have them tapering out at the end. And then that funny part plate gets stiffened by our cut profiles. And we can do that 2 times. In the meantime, we should have a plate just with the stiffeners, and we have a plate that we curved, put through typically roll benders to get that curvature. And again, we stiffen the plate with profiles. We have our basic plate. We have our 2 funny plates with the cutouts conveniently for the profiles to go through. And the rest is something like a hood to be fitted on top of that. And if you turn it around, lo and behold, we have half a double bottom for a smaller ship. That's basically the idea of assembly here. And the more you can do the forming and the welding with the robots, the more efficient typically production gets, and the better it is in design for production. And if you have more blocks, then you put the larger blocks together. Again, if your shipyard is able of lifting larger blocks, then you can make each individual block larger, heavier, and that again will help you in the assembly process. Well, typically you have then some sort of semi-automation, some sort of semi-robotation in your assembly. The more robots can do, the cheaper generally your assembly gets, but that requires typically larger scale, economies of scale, larger scale production, more sister vessels, etc. Similar lineup for assembly plane, and if you have curved panels, we'll have them typically on these pinjik platforms, so that whatever stiffener you put on is aligned horizontally, and you can use simple robots to go along and perform the welding. When you get to the end, it gets much more difficult for the robots to work. Then it makes, at least you can exploit some of the work process order, and typically you turn things around so that you can have the easy horizontal parts welded and then fit the curved parts on the existing rib structure, for instance, here in the bow. Robots, I've mentioned, robots can move from very simple to very sophisticated. Generally, any device that is programmable to perform some task automatically is called a robot. Here we see robots in a Korean shipyard in the assembly process. And what you should bear in mind is that the big red part above and all that is the robot. So robots like lots of space to have access. If you are in tight spaces, as for instance in repair, robots generally break down and you need the ability and intelligence of humans to do the job, taking longer time and typically costing more on the man hours. Besides the hull structure, which of course for your course is the main theme, building a ship involves a lot more than the steel structure, and a lot more of the cost come in the other parts. For instance, the outfitting with all the cables and all the pipes that go through the ship. Again, pipes typically are, well, at least made of metal, often made of steel, stainless steel, for instance. Again, they're standard parts that have similar processes as for profiles, for example. They're cut and they are formed, bent to then be fitted in the assembly. And typically, at least in Asian and Middle European shipyards, all that bending is done automatically with numerical control machines. Then you'll have lots of these parts, and what you'll see here is already giving an indication what is good for design for production. You see baskets of parts, and each one is needed for one outfitting unit, for one process step. So it's a bit like IKEA assembly. You have all your parts together, you have an instruction for the work to be done, possibly these days even in augmented reality, and then you do the assembly. Similar for lots and lots of pipes, cut to length and labeled to go into hopefully the right place. Again, the symbol there with the burning dollar note is saying this is where a lot of the time in the shipyard is spent, and therefore this is also very important on the overall cost and delivery times of ships. Trend is generally towards more outfitting for section. So while the section is, for instance, still in the hull, it's not just getting the steel parts, but it gets whatever it can get in terms of equipment, machinery, pumps, etc., internal cabling, internal connections, and then the whole block gets connected to the next block with pipes, electricity, etc. Setting the mood for DFP, design for production. Now, this reminds me of my youth when I did my first time work in a shipyard. That was pretty much how it looked like. We got huge drawings, folded, went to the ship, tried to make sense of the drawings, trying to find some space to unfold the drawing, typically on the floor. and trying to find the little part in the drawing that we needed now to understand what kind of assembly task was to be performed. That's not very effective in how to perform the work. We got a lot of information that we didn't need at the time. We sometimes didn't get the information that we needed at the time. So production would like to have much more of additional information that you typically don't find on these drawings, as shown here. And the extra bits help you in basically telling how do I connect to the neighboring construction, what do I need to do. If there's a lot of cross-referencing, chances are, as the English saying is, shit happens. The more complex you make things, the more give reference there, try to find that in another file, meaning go back to the office, try to get the other file, no good. What then came to be standard in modern shipyards, I would say, at least after the year 2000, maybe sometimes after the year 10 years before, is ship production booklet. So basically A4 format, where you have the drawings and you have the part list and you have the additional information and you have the assembly information, for instance, in explosion drawings. And that comes with the basket full of parts. And these days, of course, the next jump for that is that you do not have or do not need to have the paper version. You can also have that on a tablet with, for instance, augmented reality or a short video telling you this is the next assembly step. This is how it's supposed to be done. That kind of quasi 3D viewing helps enormously with being just intuitive. You don't need much mental process to see what you need to be done, what needs to be done, how to fit a part, for instance, a pipe part in the connecting other piping system. And it has all the information that the worker needs, and it also typically tracks at the end that the worker has done its job. So, as I said, DFP is not rocket scientist. You don't get a Nobel Prize for it. A lot of it is common sense and implementing that common sense from the design stage all the way into ship production. And as I mentioned, this wonderful Swedish company before, it's the same principle. You have all parts together and no other parts that you don't need. You have simple instructions. If you ever try to assemble something with IKEA, you know, it's not that simple, but the idea is that you have the instructions quasi 3D to what needs to be done. You are not bothered with things that you don't need now in the assembly process, and you'll try to minimize the number of parts and any special processes, any special skills in assembly. That's the basic idea. Let me try then to move on to how do we implement this? What are a few do's and don't recommendation in the ship? This is part taken from a whole day of training. So we will focus here only on the ship hull. So design for production, yep, a design for everything has come up in the course of time. Design for manufacturing, design for operation, design for maintenance, design for disposal. Many of these are, if not the same, achieving very the same goals. Generally, if you have a ship that has been designed for production, it will also be a ship that's easy to disassemble and to dispose of. If you have a ship that is designed for production, typically will have easy access to the parts. That will also mean it will be easy in maintenance work. You can do a lot of blah, 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 blah around design for production, particularly if you're a real aficionado of it, but I'll spare you that. I'm the type who much better learns from examples. And why do we talk about design for production? Because the way you structurally design your ship depends on the technology that is available and the technology and the materials that you use for the ship. In the old days, let's say 1900s, typically the ship hull was made still of wood. May have certain steel reinforcement rims around it, but a lot of wood was used. And around that time, or let's say 1850 to 1910 is the transition time where our ship building moves from sailing ships to steam-powered ships and moves from wood to first iron and later steel. Okay, you look at the parts and say, yeah, fine, so what? Well, naval architects like copy-paste. Naval architects typically say, I have to design a new ship. Let's take a base design, something very similar, and just do modifications on this base design. That's very much ingrained and taught in how we design ships. So if you look at the right-hand side, you see a typical wooden ship, probably something like a frigate around 1800. You see the sections and you see thin splines basically guiding the planks along the line of the ship. What you see here is a lot of curvature. And a lot of curvature is actually fine for wood, and it's really bad for steel. Then we moved and said, let's change our material. Let's move towards steel. First with riveting, later with welding. And then later on, more recently, we may have moved on to yet another material, composites, plastics. With that, we have, again, different ways of assembling, different ways of joining. Plastics you cannot weld. Plastics you glue. Welds are actually quite fine if you have them aligned with no overlap. We moved from riveting with overlap to welding with no overlap. And if we go to gluing, adhesive bonding, we'll have to go back to overlap again. So your typical steel construction wouldn't work. It wouldn't give you enough strength to transmit, for instance, shear forces. And you need to, again, change the design. If we have changes in the technology, such as laser with very little heat input and very high precision, then again, you can come up to thin steel plates and thin structures up to 4 millimeters, fine for laser. And you'll see what you see on the right-hand side, sandwich panels. This comes from the Mayo shipyard building cruise ships. And rather than having thick steel with stiffness underneath, you'll have a thick sandwich where all the individual parts are thin, and that's feasible and suitable for laser. And robot welding works fine if you have easy access and if you have simple welds. Typically, long straight lines are fine for robots. Here, it's not the day of the engineer that everybody is celebrating. It's also not a COVID-19 situation. This is actually a photo of a shipyard in Germany in a normal working day under operation. And I could play the little game and say, how many people do you spot? I think there are 5 or 6 on the photo. But what you see is there are not many people in the shipyard anymore. It's highly done by the machines. It's highly automated. And similarly, you can have machines doing the forming and the cutting, etc. How does that relate to how we should design the ship hull? Well, here's the bad news, or maybe the good news. We specialize as we move through our studies. Initially as naval architects, the university try hard to make us multidisciplinary, knowing a bit of everything. Then I, for instance, worked also for many years in ship hydrodynamics. And if you look at how the ship hull, typically the form is designed, it's designed according to hydrodynamic guidelines. It's organized by hydrodynamicists. And hydrodynamicists have their own view of the world, and it's not making it easy for the production guys. And if we bring in the production guys early on, or if the designer in his brain is not just a hydrodynamicist, but also considers the design for production aspect, we'll get better designs. Hydrodynamicists, oh, lots of changes, curvatures, streamlined shapes. Other things are fish is fine. Design for production guy says, lots of straight parts, shoebox, super easy to weld together. You have to ideally combine both without paying too much of a penalty on either part. And with a good design, you can cut down considerably on the cost. A lot of the cost, for instance, for the ship hull are determined early on in making the lines. If the lines have lots of complex curvature, that's going to cost you time and money in the production part. So ideally, simple way is talk to each other, or ideally have a designer that keeps all the aspects in his mind together. I used that a bit earlier as an analogy in saying, originally ship designs came from wood. And wood is a material that's actually quite difficult to get in a straight line, to have a straight surface. Wood is much easier with light curvature. So the barrel or the boat, you see there's light curvature, natural curvature following the natural curvature of the wood. If you move to steel, you don't want to have that. So the drum is much easier. There's curvature only in one direction, and in the other direction, it's straight lines. And similarly, parts of the ship, you ideally want to have only curvature in one direction. That's much cheaper to manufacture. So single curvature, reasonably fine and easy to do. Large and complex curvature, depending on how much curvature you put in, is often an iterative process, and it takes time and often additional energy, for instance, thermal forming. And if it gets too complex, your only resort is having casting, and that is by order of magnitude maybe 20 times as expensive as cold forming with roll presses. Brings in the concept of curvature. Gauss, you may have heard as a name, Gaussian distribution, etc. German mathematician. And Gauss also contributed to many, many fields of mathematics, also geometry. And he said, well, you have two curvatures, the maximum curvature in one direction and the one perpendicular to it. And then depending on the product of those two, you will have convex or concave surfaces, you have developable surfaces, or you have really nasty surfaces with reverse curvature. What we want to have for the hull are developable curvatures. Those are the cheap ones. Convex or concave is okay, and K smaller than 0 is a nightmare. I see, if you move towards very complex shapes in your design, then very often you have to cut pieces into smaller pieces, weld them together to just handle the complexity. If you want to avoid casting, casting, as I said before, is very expensive. Developable surfaces sound easy. However, there are only very few developable surfaces in this world. A simple body does not necessarily mean it's developable. Cylinders, cones, and parts of those, and of course flat plates, are developable. That's what we like. If we have something like somebody has the brilliant idea of using a half sphere for the bulbous bow, so we know we can't develop it. It's going to be quite expensive and tricky to get that manufactured by patching different surfaces together. The cut systems, commercial cut systems out there help you. They have functions where you can display curvature and see where do I have areas of particularly high curvature. And then sometimes the solution is to have a knuckle introduced at that part and then reduce the curvature locally. I prepared some self-study on historical approaches. Most of them failed because they were overdoing the simplification. But let's see how we can handle that in practice. Design for production can give some generic recommendations, some generic guidelines, but much of the details depend on the actual shipyard. It depends on the equipment that you have on the shipyard. For instance, maximum lifting capacity of cranes, what kind of welding robots do you have on the shipyard? To some extent also in what kind of ships do you build on the shipyard? Let's look at the global generic, always applicable parts that follow the design for production philosophy. If you have relatively short and wide ships, you have fewer frames, you also reduce generally your steel weight because global bending moments are smaller. From a production point of view, short is good. Whether that's from a hydrodynamic point of view, still a good compromise is a different topic. If you have a long parallel mid-body, that also helps you because there is so much repeatability, possibly several sections are the same on the steel side. The repeatability is good. It also means a longer parallel midship generally means more flat plates, and flat plates are the cheapest in manufacturing. Large block coefficient is fine for the application for production. Again, if it's more like a shoebox, the production engineer is happy. Small bilge radius helps you if you just use one plate that needs forming in the bilge, and then you have flat of side and flat of bottom. It again reduces the forming work, which often is iterative and time-consuming, therefore expensive. But then there are some other aspects, and we'll have a closer look at these. Casting is expensive. If we can avoid it, we want to avoid it. And I'll show you some examples of how we can avoid casting in structural designs. Double curvature is expensive. Double curvature typically means high internal stresses. And that often then means you have to have heat treatment to avoid immediate or short-term problems with fatigue cracks. Single curvature also means typically less scrap. Again, money in the pocket for the shipyard. Many hull lines can be straight in one direction. That's cheaper in production, and often you don't pay a penalty in hydrodynamics for that. I'll show again some examples. Flat is cheap, single curvature is the next best. Flat is of course perfect because it doesn't mean any forming work, not for the plate nor for the stiffness on the plate. That makes it also cheaper in the assembly because flat plates are very easy to be done by robots. Repeat, repeat, repeat. If you have fewer parts, if you can have more similar sections, then it's not just the number of parts that you do in manufacturing, for instance, in programming your CNC machines, but it's also meaning that there are fewer parts to be tracked. There's less danger, less risk that a worker will pick the wrong part. That means there are fewer errors in assembly, meaning fewer correction work spotted. That part shouldn't have been welded here. Now we have to burn it off again, get the right part, go find, burn the right part, cut it again to the right pieces. All that extra work that often is 30 to 50% in shipyards often is repeat work to correct previous action. The bow of the ship, the stem, the contour of the bow may look nice, but even if you have it straight there, then it means internally there will be an elliptic waterline, not a circular one. Again, sometimes we see hull shapes coming from tradition, and hull shapes from tradition often came from templates. Cut out plastic or wooden parts where a circle was easy, but it is not necessarily a good idea to have circular holes or circular shapes in the ship. Almost trivial. Of course, hydrodynamics play a really important role for the size of the engine, for the fuel efficiency of the ship. So we should consider hydrodynamics, but the ship does not need to be hydrodynamically optimized above the water. Hydro, water, it needs to be hydrodynamically good in the water. Sometimes above the water, some nice, smooth flowing lines mean a lot of work in production, not necessary for the fuel efficiency of the ship. Casting avoidance, think about introducing knuckle lines. Here we see an example of the general idea for the bulbous bow on the left-hand side and an actual implementation from a Dutch shipyard on the right-hand side. In the good old days, comic strips, Tintin, etc., something still 1960-ish. If you, as a naval architect, look at Series 60 hull shapes, you will see these everything round everywhere kind of ship design. Now only in historical ships. Of course, if you have a flat plate or a couple of flat plates forming a transom stern, much easier as the transom stern of this ship is above the water, any effect on the hydrodynamics. And actual design, older, not following DFP, that kind of very complex 3D shapes in the aft body. I saw them quite a few times in my work when I, as a hydrodynamicist, did CFD, computational fluid dynamics, and had to fit computational meshes to the geometry. And that was always hell. And as a general guideline, if it's difficult to make a mesh, then it's also difficult to build. Here, again, welded structures can simplify the overall assembly with next to no penalty in terms of hydrodynamics. You see here cross-section of the lines where chines or knuckles are introduced, reducing the curvature and improving the assembly, while having virtually no effect or no negative effect on the inflow to the propeller and the hydrodynamics of the ship, so the resistance and power requirement of the ship. And going one step further is something that probably really came up around the year 2000, so-called pram type stern, where you have almost a tunnel in front of the propeller, which in itself is simple. Then you have a hard knuckle and the rest of the ship moving again in a simple way, where you can imagine that in longitudinal direction there's not much in terms of curvature, very moderately, and that again makes it easy to actually build it on a shipyard. And that ends a little glimpse of DFP as for the ship hull, where you see, okay, we'll bring together understanding the material, typically steel, here thick steel, the manufacturing processes, cold rolling, thermal forming, and the welding, and the generic insight into how do we implement that. And I would say I'll stop here, stop sharing, and we can start discussing.
Okay, thank you very much, Volker, for the interesting presentation. Now the session is open for questions. Preguntas de la audiencia, bienvenidas, comentarios. Si en inglés directamente, por favor, si conocen Zoom, tienen que levantar la manito, que es una mano azul, o pueden hacer la pregunta en el chat. I will start warming up with questions. You had a slide on laser welding where you had a built-in stiffeners between the two flat plates.
The
It's
sandwich.
been some talking about sandwich panels helping production, but actually I don't have any knowledge that is actually widely used. I think there have been a couple of
No,
tests.
it's very little used, partly because laser cutting, laser welding is very expensive as a machinery. So you would need to do a lot of sandwich panels to say it's worthwhile doing that. And you should also say, hopefully I get some added value from having sandwich panels. Now we have in Germany, we have the Mayo shipyard, which does cruise vessels. The cruise vessels are very expensive, large. And for instance, there it's quite nice to have these sandwich panels, because when you put interior design, carpet or something like that, you want it to be smooth. So you don't, you save the time of flexing, eroding the weld buckle away, because you really want to have a smooth surface in the cabin for the passenger. Saving that kind of work and building a lot of these decks, it's okay to have the investment for Mayo shipyard. The other shipyard that uses is Blohm & Voss. They do Navy vessels and mega yachts, where often the steel thickness is much thinner than for normal ships. You talk a lot more 4 or 5 millimeter plate thickness for the plates, where some of the other welding techniques introduce a lot of deformation. And again, frigate, nobody's going to really ask that much how much the next German frigate is going to cost. They just raise my taxes. A shipyard like Blohm & Voss can then say, well, we need that kind of precision for the Navy vessels. These are, again, each Navy vessel is high-tech, highly expensive one. Then it's okay. For most other shipyards, I think still the cost for laser is such that it's hard to recuperate it. You may perhaps then go with an external provider that does all the cutting and forming of parts for you as they do in the Netherlands, and then put everything on trucks and send it to the shipyard. But it's that kind of thing where I think other shipyards would, if anything, give a subcontract, for instance, to Mayo, to have these deck panels pre-manufactured and then incorporate them in their overall design.
Okay, and just to run up the subject, to your knowledge, is there any provider of this ready-made sandwich plates? The technology is very expensive for the shipyards to have, but perhaps you can buy the plates already welded.
Yeah, I'm not familiar with I think Mayo cooperates with some shipyards in Germany to say, hey, let's more or less run our machinery around the clock. We don't use it enough for our own ships, so let's outsource the service to, or let other shipyards outsource the manufacturing of that kind of to us. But then you need to have them reasonably close, so you can go to the Netherlands or go within northern Germany, but you don't ship them around the globe. And I think for composites. There's some company, some like SGS, where you also have sandwich panels of, for instance, for decks in ships, but they're made of composite material.
Okay. Claudio Bobadilla, your question.
Good morning, Dr. Bertram and Mr. Salas. I'm talking from Punta Arenas, Chile, and I'm working in the polar business vessel, Mr.
Okay.
Bertram. Okay, and I would like to have more details about something that you mentioned in the presentation. That it's about the double curvature. Okay, double curvature that we see. In the first C, you say that it is not good or it's not the best for vessel.
No, it's the most expensive.
For most expensive, yeah. But okay, it's just because it's more expensive, or is we are talking about design? We have
It's
considering also.
it's more,
Sorry,
it's more expensive in the production.
only expensive. I mean,
Yeah. If hopefully you have this link to the histories from lessons from history. For instance, Peter Schenzler, I'll type that in.
and also, sorry, Mr. Is because we are see that in the polar vessel we are see a new kind of vessel that is the X-bow vessel. That I don't know if you know that.
Yeah, the Damen shipyard
yeah,
pushes that very much for reasons of seakeeping. The X-bow as such, I don't think is so difficult to manufacture, and I'm not convinced that for good seakeeping it has to have the X-bow. But Damen, I think, patented it or so, and very say, yeah, if you go. The X-bow is going to be fantastic. We see quite a few vessels designed for, let's say, Arctic cruise applications or Arctic research vessels that don't have this bow. It depends again on how much is good seakeeping really vital, or how important are the seakeeping properties of your ship. And then many others say, I'm more concerned about the behavior in ice flows and possibly mild ice breaking capabilities, and move yet to another bow design. And on the double curvature, Peter Schenzler was a colleague at Hamburg Ship Model Basin. He, I think in the 1990s, was involved in a project for Indosail, the Indosail project. That's a commercial ship to be built and operated in Indonesia, sailing between different islands. And for instance, the Indosail hull is completely made of developable surfaces and still had very good hydrodynamic features. So often it's possible to avoid the high double curvature and still without paying a hydrodynamic penalty.
Thank you. Any more questions? ¿Alguna otra pregunta? Javier Benar, te veo en cámara, pero está sin micrófono.
Hi, how are you? Nice to see you again, Marcos and Volker. Yes, we have a question on the experience of Volker. Our market is mainly on workboats, small boats around 24 meter length and less. Then, in his experience, what is better, to use longitudinal arrangement in the structure or transversal?
I would say transversal. If your ship or boat is 24 meters,
Yeah.
then you don't have, or you shouldn't have any problem with longitudinal strength. Right? Typically, when you come, I don't know, above 80 meters, longitudinal bending moments start driving more the design, and then you want to have the cross sections of longitudinal stiffness to contribute to your moment of inertia, to your longitudinal bending strength. From a production point of view, often transverse stiffeners are easier. And for something, as you say, 24, 25 meters, probably anything up to 50 meters, gut feeling is transverse stiffening will make things easier and cheaper for you.
And what happened with the catamaran's configuration? That then you have two very slender hulls. Then is another option to use in this configuration longitudinal arrangement?
I think in catamarans, the longitudinal stiffness could only be really in the bridge above, and possibly if you have some sort of like swath, some stiffness longitudinal below. I still would think that 24-meter order of magnitude catamarans you can build quite nicely in transverse stiffening. It's more there, your problem will be more in the connections. Do you use catamarans or swath?
No, catamarans is there mainly for our hulls around 18 meters, and each semi-hull are around 3 meters, maybe.
I think your key load on catamarans is local loads, not global bending moments.
Then it's preferable to use transversal configuration.
Yeah, I think if you have something like 25 meter for a catamaran, the structural design thickness is driven by local strength. And with that, even with transverse stiffening, you should have, within a big margin, enough longitudinal strength.
Okay, thank you very much.
Ok, no tengo ninguna solicitud más de preguntas, así que yo voy a hacer la siguiente. I have another question. Some time ago, we got a request from a local shipyard to do some training on thermal heating. And we didn't have and still don't have any clue on that. So we went to the classification societies, asked around if they have any training on that, and the answer was that you should go to the shipyards. And shipyards, the thermal forming still seems to be kind of an art. And I'm wondering, in this era of computing, isn't any automatic way of doing that? Because we see a lot of videos on YouTube when a guy, even in a Japanese shipyard, supposedly to be highly technological, you see an old guy doing that almost like an art. Do we have any developments?
Well, it's always very difficult for us to estimate the age of a Japanese guy. When I was 26, I think I made a mistake of asking them to estimate my age. And I think he said 49, smiling. So I never ask again. But seriously, in many shipyards, it is, yes, to some extent, an art, an iterative procedure where you have some templates and you do a bit here and a bit there and then try to fit it again. For the heat, let's say thermal forming, not the heating to reduce internal stresses that also come from welding. Let's say for the forming, I have seen a paper. It could be in the very early beginnings of Compit or Hyper, where finite elements were used. You can use finite elements to see how does it deform under brute force. You can use finite elements to say how does my steel deform under a heat field. And that was a Japanese shipyard, I think one of the large ones, with an R&D project, but we're talking about at least 20 years ago. So that R&D either was useless or has gone long now into industrial practice. I think it has gone into industrial practice. If you have that kind of computing capabilities, you can have a finite element analysis to say, I need to have this kind of heat field to get that kind of deformation, kind of reverse things, briefly getting there. And then using that information directly in a numerically controlled heating machine. I would again say kind of high tech that is not used in, to the best of my knowledge, is not used in any German shipyard, and most likely not worthwhile the investment for a Chilean shipyard, but could be a great PhD subject.
Thank you. ¿Alguna otra pregunta? No veo ninguna otra pregunta, ni en el chat, ni manito azul. Así es que we are getting to the end of the presentation. Thank you very much, Volker, for your kind willing of being with us in these difficult times. And we hope to see you in person someday in the future. Here you will be very welcome. And thank you for all the colleagues that attended this lecture on the Day of Engineering. Muchas gracias a todos por asistir. Gracias, ha sido bueno ver a algunos viejos conocidos. Javier, saludos. Y cerramos la sesión por hoy. Thank you very much. Aplauso
Thank
virtual o con la manito azul. And
have a nice weekend. Bye-bye from Germany.
Bye-bye. Bye.
Bye.